Okay, and did you see that you had a question by Leonardo asking if decreasing gamma would it make it better? I don't know, it was just before the break, but I'm not sure you answered, I don't know.
No, sorry, I missed it. Because it doesn't automatically scroll, so sometimes I miss the question. So gamma is usually considered as a parameter of the problem and not of the algorithm, in the sense that you should be able to claim that your problem has a specific gamma that is justified for the problem that you have to solve. Now, truth is that in practice, the gamma is oftentimes something that you can change, and so in problems like this, where the one of the negation, where you don't really know in advance how many steps it might take to reach the goal, somehow you should just set gamma as large as possible. There's no reason to set gamma even smaller than 1. So in practice, most of the time, the gamma that is chosen is a large one, like 95, 99. It's true at the same time that if the problem admits it or allows it, a smaller gamma allows the learning algorithms to converge faster. So usually the smaller the gamma, the easier the problem, both to compute optimal solutions and to learn optimal solutions. How much the priori knowledge that you have of the system might help here? Well, I think so there are two types of answers. So either it's your prior knowledge is super specific to the problem, and in some cases, so the handle that you have is on the definition of the state, the definition of the action space, the parameters of the algorithm, and the design of the objective, like of the reward function, these kind of things. So in some cases, it does help, and it can be translated into these parameters effectively. In some other cases, it doesn't. In some cases, it's maybe not a super specific prior knowledge, but it allows you to know that the problem belongs to a family of problems. Yesterday, I think at a certain point, I mentioned things like linear quadratic controllers. So there are in control, in particular in operation theory, operation research, there is a lot of literature about finding, in our terminology, would be specific MDPs, families of MDPs that have so specific structures where that you can try to leverage in your algorithms. Let me just give one example. So one prior knowledge that oftentimes you have, or at least in some projects you have, is the monotonicity of the value function with respect to some state variables. The typical example is portfolio optimization or energy management, or something where time is a resource. In all these problems where the state might be characterized by a lot of variables, including these variables, then usually you know that the more time you have, the more money you have, the more energy you have, the more space you have, the better off you are. And so you know that at least with respect to some variables, your value function is monotone. Then you can try to enforce this constraint into your learning problem so that you kind of reduce a little bit the effect of noise. So if you're quite confident about a value in a state, and then you end up in a state for which the variable of interest is bigger, then even if by noise, say you might be convinced that the value is lower, then you know that it cannot be lower than the previous value, right? So you can enforce somehow some constraints into your scheme, capturing a little bit of this prior knowledge. So there are a few examples of this type, not that many. And honestly, reinforcement learning also suffers from the general purpose nature of the field, which doesn't want somehow to leverage specific families of problems, because it's a little bit AI. So you have an agent, you learn, period, right? So defining families of problems is for engineers, which I think is also not a very good mindset, but that's often the reason why you will see very rarely in RL families of MDPs that are specific in some sense, while you will see much more often in operational research or in optimal control. Okay, so hopefully in the meanwhile, everybody is back and you had access to the notebook that we are going to use. So can you just confirm that you have it on your laptops? So the title of the notebook is QL Draft. So it's a Colab notebook, so that at least you can load all your stuff directly. There's nothing to install on your local on your laptop. So,
Alessandro?
Yeah.
Just one question. For people here in the room, maybe they are not connected to BBB. Eventually, is your Colab accessible from your PDF?
It should be. So if you download the new PDF, okay, let me show. So if you download the new PDF and you scroll to the last slide, there is this taxi problem, hands-on session, and this should be a clickable thing.
Okay.
This link. So yeah.
It's okay.
See that? Okay, great. Okay, so let's look through this, and I will, skip a lot of details which are not that interesting for us, which are really more about the infrastructure and the exercise. So we will really try to frame this as an exercise so that you have the time to go back to the slides, reason a little bit, is to implement really the Q-learning update and the Q-learning, let's say, interaction loop with the environment. Okay, so let's, and the problem will be the taxi problem, on which I'm wondering, maybe, okay, let me at least show you what it looks like. Okay, so this part, we don't care, all the libraries, we don't care. Maybe just for your curiosity, here we are going to use an environment which is called GIM. So it's a library that is installed up here. It was initially released by OpenAI, and it contains a bunch of test beds for reinforcement learning, from easier to more difficult, and it's still nowadays often used for validating algorithms in reinforcement learning. So here it's just a bunch of imports. So this will be just to showing the video of what happens to the agent. Here it's just wrapping up a little bit the things that we said about MDPs, optimal value functions, and so forth. So first we load the specific environment that we care about. In this case, it's the taxi environment. And so this, I will not talk about it, but I will just focus on the picture here. Not the fanciest, as you can see, but it helps us at least in illustrating what the problem is. So it's still a navigation problem. The points here are somehow, the blank parts are states which are freely accessible. The dashed parts here are walls, and these points are just separator between freely accessible states. So it's really just a grid, basically, with some walls here in between. The agent is this kind of highlighted cursor. It's not the R, but it's really just a highlighted cursor. And the R, G, Y, and B are 4 different spatial locations for in this navigation. And the objective of the agent actually is a taxi driver, and it has to go and pick up a passenger, drive the passenger to the desired destination, and drop down the passenger. The RG, Y, and B locations are the possible pickup or drop-off destinations. The one which is, if I recall correctly, the one which is a little bit in bold here, it should be the the one in bold is where the passenger currently is, and the one in color is the destination. I hope I'm not mistaken. And the state space is basically the position of the driver of the taxi, the position of the passenger, the destination. And so this is I think it's a 5x5 or something, this grid. So it's 25 states. And then for each position, there is where the passenger is, which is either of these 4 locations or in the car, and the destination, which takes one of these 4 values, right? So we have 25 locations for the driver, 5 locations for the passenger, 4 locations for the destination. You do 25 times 5 times 4, and you don't get 500, but yeah, maybe I'm missing something in the range of variables. But anyway, so let's say that it's 500 discrete independent states. And we have 6 actions, which are the cardinal actions, and 2 actions which are about picking up a passenger, which is successful if the passenger is in the same position as the car, and drop off, which is successful if the passenger, if the action is executed while the passenger is on board, and the drop-off action is done at one of the location, which is the destination of the passenger. Every time an episode terminates, the environment is reset with a new position for the car, a new position for the passenger, and a new destination location. The rewards, I don't remember. Honestly, I forgot to check. We can check together because I don't remember exactly. Yeah, okay. Yeah, so the rewards are -1 every action, -10 when we bump against the wall, and then I think it's a reward of 10 when we complete successfully the task. So you see that, for instance, in this case, this guy is moving around, and here you can see the action that I'm doing. Southwest are the actions: pick up, drop off. From time to time. This is a totally random policy, by the way, so it's not doing anything reasonable. And it's just taking any of the 6 actions at random. And when it's a pick up or drop off, it's not doing anything because the passenger is not on the same cell. And when I take an action on navigation, I think the dynamics is almost deterministic, or maybe it's even deterministic. And when I bumped against the wall, I get a -10. And otherwise, eventually, by randomness, which you see it's not very likely to happen, I end up in the cell of the passenger, picking up the passenger, and then navigating to you see here, and I ended up here. Oh, I picked it up. So you see now it's not bold anymore. So now the passenger is here. And I dropped it off here, which it's not the destination, so it's not getting any reward. It's getting a reward of -10 also when it does pick up or drop off in locations where the passenger is not. And eventually, again, I have to be lucky enough now to go back here, doing pick up and dropping off at destination B. So this is the problem. Not easy. But let's hope that we can solve it by Q-learning. So now I'll just stop it here because otherwise, let me just maybe just for the sake of it, see how many time steps it takes to randomly. Yeah, you see that by just doing things at random in this specific case, it took 752 steps to actually complete the task. Which of course is a lot, but it's just a matter of luck. I wait for a while and eventually I will be doing the right sequence of actions. But of course, it's definitely not the right way to go. So Q-learning is implementing this update rule. So that's the one that we have seen so far. So the way that it's coded. So let me know if this is too small, because of course people seeing the share screen and it's fine, but if it's projected, maybe it's small. So just let me know if it's readable. Okay. Yes. So I define a class which I initialize with the number of states, number of actions, initial learning rate, initial epsilon parameter for the exploration. I initialize the Q table. So here is the Q function, but in this discrete case, I have finite number of states and finite number of actions. So it's really just a matrix. It's a table, as I will call it Q table. And then I have basically three methods. One is policy, which just returns in the state the action which maximizes the Q value at the state. Or there is a simple action method, which is actually performing the epsilon greedy strategy. So I'm drawing a number at random. If it's below epsilon, so with probability epsilon, I take a random action among the available ones. Otherwise, I will be calling policy again, which means I will be taking the greedy policy. So these you can, reframe it as greedy policy and this as epsilon greedy policy. And then there is the updated function, which I haven't completed. So if you have downloaded the previous version of this notebook, you already have the answer there. But please play the game correctly and try to see what to implement in here. And then we have, so this is the Q learning algorithm, and we have to invoke this algorithm appropriately. So the way it's going to work is that, okay, we set the parameters, we set both of them to 0.1. And here in the update rule, you can decide to decrease them or to keep them fixed. Suggestion as the first version of the code, just keep them fixed. So don't decrease neither alpha nor epsilon. Problem parameters here set the gamma to 0.9. I could put any other number, but I put it a little bit smaller than what I should just to make it converge a little bit faster. I create the object Q learning. Then I define the number of episodes that I want to run. And each episode, so this is the loop over episodes, it's resetting the environment. And then until the environment is not terminated, I will be keep executing actions, right? So what I'm asking here somehow is to implement. Sorry, I'm saying this is the loop over episodes. This is while the episode is not terminated. You should say which action you pick. You should collect this, and you should invoke the properly implemented update of the Q learning. So this is, again, it's not an exercise in the sense that there's not an evaluation, it's not a class, but it's really for you to look back at the slides and see what it would look like. So just for information, sorry, let me just grab one line here. So this is the way to invoke the simulation of one step into the environment. So the environment has an inner state. So it's already initialized from here. So you see that this is the way I get the first state of the environment. So I don't need to pass again this information. And whenever I take the step, I just need to call the step with the appropriate action, and it will return the next state, the reward, and whether the episode is done or not. So now here you have to properly design how to pick the action and how to update the Q values in the class Q learning. Is everything clear? Are there questions about this? And then I can give you a few minutes, and then maybe we interact a little bit and we look at the solution, and then we play around with it. Just to have a feedback. Is there anybody who's advancing? Is there any question? So, if everybody's done, then we can directly look into the results. If struggling with some specific points, we can discuss about it. So, is there anybody who's done with the implementation and even try to execute it, either in the room or on the chat? Not yet. Just for reference here, I've been running just a random policy again, and every 100 steps it displays what is the number of steps to reach the goal for that specific episode. And so you see it's very large, and sometimes it might be super lucky, like 67, but in some cases it might even get up to 8,000 and basically never really reach the goal. I think it's even capped to the length of an episode somewhere. I don't remember where it's coded into the environment, but just to confirm that somehow the random policy is not good. And so what you should be expecting from Q-learning is much smaller numbers eventually. So maybe not right away, because we'll need to do a little bit of exploration, but eventually we should be able to get better ones.
Okay, so I didn't update the n steps, so actually I'm printing n steps equal to 0 at each step, but it looks like it's working.
Okay.
So I used Epsilon policy as yeah.
Mm-hmm. So the action here, how do you generate it?
The action.
So
it's just a QL that sample action of state.
And we execute the action. So this is out. That's about the environment. Then I guess you can call the update. And you pass on the information that we need. Current state, the current action, next state. Word associated, the gamma parameter, and whether the epsilon is not attached. But this needs to be implemented, of course. And then you look back. Do you do anything else in this part?
I beg your pardon.
Do you do anything else in this part?
Oh no, that's all I did. No. I update the state, like state equal to next state.
So this can be done two different ways. Either you directly do it this way, or you recover the state from the environment this way at the beginning of each step. This way, sure. So, even know.
Oh, okay.
Here, I did the same as you were suggesting. So this part is relatively simple. We just take the explorative policy, execute the action, we update Q-learning, and we just update variables. Okay, so let's move to the update of the Q table here. There is a subtlety that I haven't discussed about, so if you got it right, it's great, but otherwise it's normal if there is some subtlety that is needs to be corrected.
So shall I say what I put in the function?
Yeah, since it's very simple, I think we can try it this way.
Okay.
Might be a little bit awkward, I realize, but let's try.
Okay, so I put 1 minus alpha dot self Q table of state and action.
So like this?
Yes, but actually it's self dot alpha, but yes. Plus self dot alpha times rewards plus gamma max of self dot Q table of next state. Comma and like all the actions, all the possible actions, and minus self. Well, the current state and action. Self dot Q table state and of state and action.
Can you just double check this part?
Yes, I think that's what I put.
So let's just contrast it with the equations that we had in the slides. Just check. So let's take this one. So here it's the previous estimates plus alpha and this difference between R plus gamma max minus previous estimate. So here maybe one thing that, if I understood correctly, it's not...
Yes, it's next, yes, indeed it's next state and not state.
No, wait. So the first term is without the alpha. But this one doesn't need anything. So it's the previous estimate plus alpha, so alpha, times reward plus gamma max in the next state. So this is it. Reward plus gamma maximum of the Q table in the next state minus previous estimate. That's the way we can do it. Now, as implementation detail, usually I don't even know whether it's strictly needed in this setting, but usually we do different updates depending on whether the episode terminated or not. So let me just check that I do it in the same way that I've done here. Yeah. So when the environment terminates, it basically means that the next state is a state where I cannot do anything, right? It's a state which there's no action, there's nothing I can do, no reward. And so somehow to be sure that, things don't get weird, what we do in the case that we are in this part where in the terminal state is basically to remove this part, because basically the only thing that I care about is the reward that I obtain by achieving that state. But from that state on, there is just a zero. There's nothing that I can do anymore. So usually we use this type of formulation here.
Okay, I did not do anything in the else. I had the if done, if not done. But
okay. Yeah, so basically when it's done, it's just a minor modification of this one, where you remove the value of the next state. So that's and again, it might be even the case that it works in any way because we initialize the Q values to 0, so it's gonna be 0 because in that goal state we never updated the Q values, and so the Q values remain at the initial value. So even if we execute this, we will be getting always 0 from here, but it's better to be a bit more explicit and separate the two cases. Okay, right. So there's nothing else as far as I can say. So we should be good to go. So this we execute, this we execute, this we execute. And now, as we can see, the length of the episodes becomes shorter and shorter, in particular from, even just a handful, let's say, a few hundreds of states, things start getting better and better. And eventually we have small numbers. Of course, I cannot say, and I will never be able to say, whether this is the optimal thing that I can do. It's very hard. How do I know? And in particular, the fact that I see different numbers, it's due to the fact that the initial configuration episode per episode changes. And anyway, I'm executing actions which are different, right? In the sense that since I have a residual exploration embedded into my algorithm, anyway, the way the algorithm behaves is not always the same. Just by randomness of the epsilon grid, it might change over time. So let's just try to see a little bit what it looks like. So, for instance, this is just one example of one episode. When we picked up the passenger, we go to the destination, we drop off, done. Right. So this is just a random example. Here I'm taking a random initial state, and we can see that now the initial state, the passenger is here. So I get here, I go down, pick up, move up to the destination, and complete the task. So again, I cannot claim strictly that, for any initial configuration, I will be executing the optimal policy, so the shortest path to all the things. But I can try to simulate a few episodes, and I will see that most of the time it will behave decently well. So this is a good example where things overall converged to a good policy. Maybe the Q values didn't really converge to Q star, but this doesn't mean the policy associated to that might not be good. There are cases where maybe the Q values did not converge very well on states that anyway they're not very likely to happen. And so I really don't care about pure convergence there. What I care about is that in states that are more frequently visited, my policy is going to be the good one. And just to get a sense of complexity, you see that even if I stopped at around after 1,000 episodes, probably the policy was already kind of decent. It was not that bad. So, of course, to consolidate the learning and having better and better performance, it's better to run it for longer, but otherwise it seems like it's kind of okay. Now, what I would like to ask here, so first, a feedback on your side. So is this solution clear? Does it trigger questions about how to implement the algorithm, how the algorithm works, about how we run experiments, generally speaking, in reinforcement learning? So first this. So I would like, if anybody has any feedback in this sense, is it clear? Also on the chat remotely. Okay, great. So it seems like it's kind of clear what we are doing and how we are implementing the learning algorithm here. Now let me ask you just a couple of questions. So just to see also, understanding a little bit the different ingredients. So here I set an alpha and an epsilon, so the learning rate and the exploration factor to 0.1 constant. If you have to guess and then maybe try to run it, if we change these values, what do you expect to change in the behavior of the algorithm? So first, if anybody has any opinion, and then we can try. So imagine that I take a learning rate, so it's constant, so I'm not decreasing down to 0, and instead of 0.1, I set it to 0.5. What could I expect in positive, and what could I expect in negative in the behavior of the algorithm? From the chat, Johanna says the algorithm would converge faster, but maybe to a local minimum. That's a great answer. So as far as the learning rate is concerned, we update more. So we take into consideration more the temporal difference errors in updating our Q values, which means that we drift away from the initial values fast, but possibly we keep updating a lot. And so in particular, if the environment is stochastic, this might be a very serious issue because we might be just integrating noise. So also the answer, less robust, much faster, is definitely correct. So we might not be converging to something good, or anyway, we might not even be very stable in the behavior because we keep updating a lot our estimates. What about and this is a little bit more subtle, what about the epsilon parameter? So the epsilon is saying with how much probability I pick the action that I believe is the right one, and the probability with which I take just a totally random action. What do you believe would be the impact on the learning, and in which part of the learning? In case we increase epsilon, we explore more, therefore we converge slower. This possibly right answer. Actually, I don't have an answer. I mean, I have indications of what could happen, but it's very subtle, actually. There is a few people typing, so just wait. The average number of steps at the end of the training would be greater, I think. Okay, that's also a very good answer. Maybe the convergence lowers for the last iterations of the training. Okay, so let's, since we will not have the time to go through the exploration part of the course, let me just take a couple of minutes to discuss a little bit about it. So in some sense, imagine epsilon equal to 1. I take completely random actions. We have seen that in terms of the length of each episode, so total time I spend interacting with the environment, which is our order of complexity somehow, it would be much worse. Right? So I would have very, very long episodes where I just do things at random. But if I look at the Q values, now the Q learning would be provided. So remember, the Q learning is an off-policy algorithm, so it doesn't really care about the executing good actions. Actually, the more explorative the actions are, the better for the convergence of the Q values, because I update. So remember that I do this bootstrapping. So I update the Q values in this state with the Q values of this state. But if this state has never been updated, my Q values will be bad. So I have to get to this state very often so as to do good updates. So in some sense, the more I explore, the more intuitively, and this is not formally 100% correct, but more I explore, faster the convergence will be for our algorithm. At which cost? Well, at the cost that during the training phase, I will be doing something which is really, really bad. And so now and it's really just to hint to this question in reinforcement learning, we enter into the question of the setting of the training setting that we have for our algorithms. So there are settings where basically I have just big simulator, a lot of time, and the more I explore, in some sense, the better. Because the convergence is going to be fast, it's going to be more robust, I cover very well all the state space, all the actions, see everything that can happen, very happy. And at the end of my very, very long hours, days, weeks of training, I will give you a policy which is good. But imagine that I'm in what we usually call an online learning setting where, I have to train a recommender system. Well, the samples that I collect are the samples that I collect by trying things, by displaying things to the users, right? In terms of items, recommendations. And if I do just uniform exploration, you can guess that I will not even get to the point of having a lot of samples. All the user will just quit my platform. I will be losing a lot of money. I will not learn anything at the seat. Right. So in the case where I care about the performance that I do while I'm training, and so now I'm doing training and testing at the same time in some sense, because I want to execute actions which are good. But in order to learn which actions are good, I need to explore. But the more I explore, the worse will be the actions that I execute. So again, there is very difficult trade-off between what is usually called exploration and exploitation, which somehow is the justification under the fact that we usually take epsilon very large at the beginning and then we annihilate it down to zero. Because this way, at the beginning anyway, we don't want to exploit the things that we learned so far because we haven't learned anything. We just want to explore. So epsilon very large. And later on, as we learn more and more, we want to be more cautious and actually execute actions that are rewarding. And so I will drop epsilon towards zero later on. So if you want, you can try a little bit this evaluation. We will be doing it offline so that we move on with the other algorithms. But just as an exercise, you can imagine to do the following. So you see that now we have 5,000 episodes of training, and then we do the testing. So what you could do is to do the testing after 100 episodes, after 200 episodes, after 300 episodes, and so on and so forth, and measure how good, if I stopped after 100 episodes, how good would be my policy. And you will see that the larger the epsilon that you put, on average, your policy that you learn will be good, but your episodes will be also very long. On the other hand, if you measure your performance in terms of the reward that you collect on the training episodes, then if you set epsilon too large, you will get a very poor performance because you will just do things at random. But if you take epsilon too small, imagine zero, well, again, I will be just doing things at random because I don't explore and I don't learn anything. And so you will see that in that case, it's a little bit more tricky what is a good parameter epsilon. Again, this is just to hint to a full field of very active research in reinforcement learning and even beyond, which is about exploration, exploitation, so on. Okay, so this was the first really hands-on that we had on an algorithm. Then we're gonna I will try to keep it short so that we can jump also to the practical session also in this case. So I would like to see how all the algorithms that we have seen. So we have seen TD learning, actor critic, and Q learning. So these three algorithms are also at the basis of the more, let's say, modern reinforcement learning algorithms, or some people would say deep reinforcement learning algorithms, where we also introduce some form of approximation into our Q values in order to manage problems that scale beyond the 600 states or 500 states that we had there, problems that possibly have huge number of states or even a continuous number of states. And this is again the topic of approximate reinforcement learning or deep reinforcement learning, like is more commonly referred nowadays. So now we want to focus on this last item here. We have large or continuous markup decision processes of which we don't know anything, and we want to learn from interactions, and we also want to learn efficiently in the sense that if I have a large number of states and I have to learn a Q value for each single state, I will never be able to do it. Just as an example, let me take this one. This is, again, a very famous baseline in reinforcement learning. It's called the mountain car. You have a little car at the bottom of a valley, and it's underpowered, which means that if you go full throttle on the right, you would not reach the goal. And so you have to do a little bit of swing up type of strategy where you gain in speed by just accelerating this way, then using gravity, and then accelerating this way, then using gravity, and so on and so forth to gain enough velocity to reach this speed. So the state space is basically the position on the x axis and the speed of the little car. The actions are very basic. It's -1 if I take full throttle in this direction, +1 if I take full throttle in this direction, or 0 throttle if just don't push on the accelerator. The reward is always -1, except when I reach the terminal state here, which is set to 0. So basically, the reward is not informative at all. Whatever I do, I observe everywhere -1, -1, -1, until by chance, at the beginning, I will reach the reward of 0, and then I will realize that, okay, maybe there is something good in there. The dynamics is just standard kind of dynamics on this type of slope with the velocity and speed which are updated. And there is also a little bit of randomness in some of the components, but we don't care about it somehow. So just to illustrate, the optimal value function for the problem, so the V of S, V star of S, S again, it's a variable which is position and velocity, looks like this. So you see that it's not even very smooth, right? I mean, here it has a huge discontinuity. Here it's kind of smooth. It has a very complicated shape. So, it's not that it has a nice, obvious parametric form, right? It's not a plane. It's not a paraboloid. It's complicated shape. And actually, I don't even know how to write it in an explicit form, honestly. So this is a difficult problem, right? If we want to estimate value functions, or if we want to compute policies, it's definitely a non-trivial problem. So the way we will usually approach it is to say, well, we try to approximate either of these ingredients. It can be value function, it can be action value function, or policy, by a function approximator. So what do we mean by that? I mean that we will take, and now I will make it also more concrete, but we will just define, depending on the things that I need to do. For instance, if I need to work with algorithms that work on value functions, I will say that my value functions lie in a space which is formalized by this parametric form, V theta of S. What is this? Well, it can be a neural network, it can be a linear parameterization. So this theta represents all the parameters that, once fixed, define a specific function. And the function remains a mapping between states to a specific value. Similarly, for action value functions, it will be, imagine a neural network which takes as input S and A, and it returns a value in output. And the thetas are, again, the parameters of the neural network. Usually, I try to pick parameterizations which are smooth, so that I can they're differentiable, and so I can compute the gradient of them. And this will be very handy when I have to run my algorithms to update my value functions or action value functions. Similar thing for a policy. Policies, we know they can be deterministic or stochastic, or discrete actions or continuous actions. So depending a little bit on the type of policies that I have to evaluate, I can, again, parameterize them somehow. So for instance, you can imagine, again, a neural network. I take as input an image. So the state can be as complicated as an image. I do a bunch of, I don't know, CNN, whatever things you would like to do. Then let's say that I do a last layer, which is just fully connected. And at the end, I have as many output as actions, if I have discrete actions. And the policy will be just a softmax over this. This is an example about how to parameterize a policy. And of course, all the parameters are basically all the weights of this neural network. And I will try to find the theta such that pi of theta will behave as close as possible to pi star. So now this will not change, right? I mean, this is still the overall objective that I have. So this I will skip it. So let's just try to review a little bit quickly how the algorithms that we have seen translate into this. So in the sake of time, I will be just talking about this one and this one. I will be not talking about these methods because we are a little bit behind in time, and I would like to at least look a little bit to the implementation. So actually I will work on this, and if we have time, we will look at this. So value-based methods. There is an easy way to translate, and I'm hand-waving a little bit here, but translating the temporal difference algorithm that we have seen for policy evaluation into a sort of gradient descent algorithm. So imagine that we are back to the policy evaluation. Somebody gave me a policy. I run the policy for a while, let's say n steps, and I define a loss function which looks like this. So it's a squared error. Maybe let's look at directly this. It's a squared error. It's the difference between v theta in st. So this is the loss evaluated in a specific state after observing this transition somehow, and given that I want to optimize over a parameter theta. So you remember that the temporal difference now sign apart was something like R3 plus gamma V of st plus 1 minus V of st. Now we are doing the very same thing, but this is now a V of theta, and we would like to find the theta which minimizes this distance. But we do something funny, and I will not justify it. It takes a bit too much time to enter into the details. Here, I will fix the theta to the one that I learned so far. So this is the theta that I want to optimize for. It's the parameter of my loss function. And this, I take it as if it was supervised learning. Right? Somebody give me this target value. And what I want is to approach this target value as much as I can. So I want to minimize this squared error. And more appropriately, usually I will try to minimize the mean squared error. But let's look at the single step update. So previously, the single step update of TD was this plus alpha. The signs are swapped. Here there is a minus and this is swapped. But it's just that this looks more like a gradient descent. So RT plus gamma V hat st plus 1 minus V hat st. So this was the TD update. So let's call it exact TD. So the approximate TD version is exactly the same, where the update rule now is derived as taking a gradient step of a mean squared pseudo loss. Let's call it pseudo loss. Why pseudo loss? Well, because again, here I'm doing something funny. I'm saying that the current theta, I use it and I fix it to evaluate the value function in the next state. Now, it's quite simple that you see that if I take the gradient of this, there is a 2 bumping up. I have this times the gradient of this, right? So that's the reason why I obtained this equation, which contains here exactly the temporal difference as before, times the gradient of the value function with respect to my parameters theta. And it's relatively easy to see that if I go back to the exact case, in the sense I have so many parameters, as many parameters as states, then this gradient here would be equal to 1, and then this goes back to TD. So this is just to say that it's not a different algorithm. It's really a generalization of the original algorithm where I have a parameterized value function. So this is basically now the equation that I have when I want to do, after one step, the update of my parameters. Unfortunately, again, this is not properly set the gradient method, but I don't want to enter too much into the technical details. So we don't have the time, and it's quite intricate way of deriving it, honestly. So I will just try to provide the intuition. Well, but then we can provide the same intuition to derive approximate Q-learning, because approximate Q-learning, we said that in the end, it was just doing the same thing as TD with just action value functions and with the specific target here. So we do the same trick. We say that we want to find the Q theta, which minimizes this loss, where this function here is fixed to the one that I had at the previous iteration. Take the derivative of this, the gradient of this, and I obtain the Q-learning approximate version that with respect to the one that we had before. Again, the signs are swapped just to make it look a little bit more like gradient descent, like minimizing a loss. So in the end, I can take whatever I was doing before, and I just replace the learning update that I was using before to this new rule. So you can take exactly the code that you had, multiply by the gradient of the Q function evaluated at the state action that you're updating. And from the Q learning that you have implemented before, you have the approximate Q learning algorithm. And that's it. I mean, it's as simple as this, except for the fact that this algorithm doesn't work. It's unstable. It's proved to be, in some cases, divergent. So it's just a nightmare to make this algorithm work. And that's the reason why for many, many years, the reinforcement learning community somehow focuses on trying to find different algorithms, different type of function approximators, stronger guarantees, and so on and so forth, and implicitly rejecting everything that was based on this type of algorithms. Because again, I can take a super simple problem and show you that this algorithm diverges. And even trying to, when people were trying it in practice, it was very brittle, very unstable, and usually was not working at all. Until the era of deep learning somehow, where people said, oh, but what is the secret of that? First is to have a lot of samples first. And then people came out with things that, not in a dismissive way, I would call it hacks, to make this algorithm more stable and performing better. So I call them hacks in the sense that they look like I'm just taking this algorithm and I'm tweaking things here and there, and I will show you what it looks like, the tweaked version of it. But indeed, there are things that are responding to very well thought principles, although again, we don't have any theory supporting that the resulting algorithm is the right thing. And to some extent, in practice, it still remains a bit challenging to make it work, but we had exceptional outputs out of this variance. So, let me maybe just jump directly to what the final algorithm looks like. And the final algorithm looks like this. So it's called DQN because it's Deep Q Network algorithm. It's basically Q learning with a function approximator, which usually it's a neural network. And it contains all of these ingredients that I mentioned. So let's now look at what the algorithm looks like. I execute an action as before. I observe the same samples as before. But then what I do is not to do an update with these samples, but I first store these samples in what, in a very imaginative way, in RL is called experience replay buffer. It's a data set. I'm just, executing a bunch of actions in the environment, observing a bunch of states, a bunch of rewards, compile a data set, call it D, and I'm done. So you see that I'm taking a little bit more supervised learning approach, right? I first build a data set. Then what I do is to minimize the mean squared error. So remember that here I was saying that we are minimizing this error on the sample as T. But now if I have a lot of samples, what I would be doing is just going to minimize the average error, right? So it's T minus blah, blah, blah squared. And here I'm just doing this. So I'm no longer asking each update to be in response of one single step. So in reinforcement learning, we were saying I take an action, I observe something, and I update my estimates right away. This way says, no, first collect a bunch of samples, store them in a data set, and then try to minimize the average squared error. The way to minimize the average error over the data set, it's like in deep learning, in the sense that what we actually do is to do mini batches. So we extract a random subsample out of this, and I compute just one step of gradient. So if you want, it's just SGD with mini batches over that specific loss functions that I mentioned before. And the loss function, again, you remember that it was defined with something where here I had the maximum over the Q value of the theta, which was the previous one, right? So I fixed it. Here I go a step even farther. I say that I freeze a target network with theta bar that I will use to compute these target values. And then I will keep using the same theta bar even while I update my thetas. So this is theta, sorry. So I keep updating my thetas for a while. I keep looping this one. And from time to time, I will adjust my Q bar and I will, so my theta bar, and I will update it by taking the value of theta hat. So in some sense, what I'm doing is to say, pretend by fixing theta bar, what I'm looking at here is just supervised learning. This is a target which is evaluated based on data which belong to a data set. I run SGD on my data set, and that's it. I keep doing my updates for a while. I have a supervised learning problem, and hopefully after a while, my Q hat will tend to approximate these samples as well as possible. But then from time to time, I also remember that, well, I'm actually doing reinforcement learning. I'm not doing supervised learning. So this Q theta bar should be my Q theta hat. That was the real Q learning update. And so what I do is just update it this way from time to time. So all these ingredients, they look like, I'm not really doing anything, right? I'm just taking the previous algorithm. Instead of updating every step, I update from a bunch of steps. I use mini batches drawn at random from a data set. And then I update my target, not at every step, but in phases, in epochs. Actually, it turns out that all of these ingredients are super effective in making the overall algorithm much more stable, much more robust and performant in practice. I will illustrate this through this example, and then we move to the code, and then we will have to wrap up. Unfortunately, we're a little bit late, but at least I want to work out this example. So there is this game of Atari that, as we mentioned before. So how do we do nowadays, let's say, reinforcement learning? So the way we do it is to say, okay, I have an image as input. The first thing that I do is to massage a little bit the image. So typically I remove the colors. I know that the problem doesn't really depend on the colors. So let's just simplify it. I put a grayscale. I crop it to an 84:84 image so that it's squared. We know that, this is very nice for CNN and then computer vision. So let's do that. So this is the first image processing that I do. Then I have to define what the state is. And you remember that this problem here from yesterday, it's no Markov if I use just one image. Okay, so I will stack these pre-processed images from the last 4 or 5 steps into one big tensor, basically, which is my state definition, and will also include the actions and the rewards into the state. Why not? I mean, it's just a little bit bigger, but here we are not scaling anymore with the number of things like before. Here we are going to do approximation anyway. We stack all these things together, and we call this the state. So it's the 4 last frames, both frames in terms of images and actions and rewards. And then I define, just a nice and very much computer vision inspired architecture where I take as input basically the image. I do all my pre-processing, my grayscaling stuff. I have a bunch of convolution layers, have a bunch of fully connected layers. And the output of the convolution layer is a vector of the dimensionality of my actions. So move the joystick up, move the joystick down, or diagonal right up, and so on and so forth, or press the button, or move and press the button. Because again, this was an Atari game where you had the joystick to maneuver to get this stuff. And that's it. Basically, this will be my action value function in the sense that it's a function that takes as input an S, and it returns a vector Q of S dot as output. Then I use, so all the things that are in between here are my parameters theta. I have this very neat thing that I can easily implement in a deep learning terminology, because this is basically the only RL part. So I have to interact with the environment, do actions, collect states, and so on and so forth. But once I plug it into a data set, then this part here is just a standard routine for any deep learning algorithm. So you have attended a course on deep learning by well, so I hope that this kind of rings a bell somehow, recognizing that this how we can implement this. And then, okay, we have again to put back everything into a RL loop and remember from time to update things. So just to illustrate why this is good, this chart is now hugely surpassed. So this, I think, is even maybe from one of the original papers on Atari. So here on the x-axis, you have a bunch of games in this Atari platform, and on the y-axis, you have by how much somehow the performance of this algorithm performs compared to, let's say, human level players, and so 100% means that it's on par with the humans. And if it's above, means it performs better than humans, and below means it performs worse. So I think by now, if you just spend a little bit of time, even actually in Montezuma Revenge, which historically has been one of the most difficult ones, probably this human level threshold is going to be maybe around here, or even old games actually, which means that basically we reach the stage where the learning algorithm with a lot of samples, we're talking about millions of frames, hundreds of millions of frames sometimes, it can learn a policy that when used in testing, it's actually performing better than a very good human player in these games. So here there's no world champion because there's no tournament of Atari, but similar technologies probably you heard in the news. Beating Go or algorithms, so this AlphaGo, or algorithms like AlphaStar beating players in StarCraft, and so on and so forth. So let's say that this is just to fast forward that all the things that we have seen with a lot of good ideas can be made much more effective in practice. So let me just give you at least the reference to the code if you would like to have a look. So hopefully the link this time is a good one. Right. So this is the code associated to this DQM, so Deep Q Learning algorithm. It's based on PyTorch, the code, but somehow you can, even if you don't know much about PyTorch, it doesn't really matter. I just want to skim through the interaction loop here. So the interaction loop is the same as before in the sense that we take an action, and in response to that action, we will observe a state. But now, whenever we observe a state and a reward, we will save them. So you see that here there is as much as before the step action, but then we store them to the buffer first. And only when the buffer reached a certain size, then we will be doing a step of learning, of real learning, which means we will sample a mini batch. So this operation is just sampling a subset of the transitions. I recover all the states, next state, actions, rewards that were stored in this mini batch. I construct the targets as we mentioned before. So you will notice somehow, a very similar scheme as in Q-learning. We have the reward plus gamma, maximum of the Q value in the next states, according to the current neural network that I have somehow. I compute the targets, I plot them all together, and then all I have to do is to compute the loss, run the optimizer over this, do a backward step, an optimizer step, and that's it. Right. So if you're familiar with PyTorch, I don't know if you use PyTorch during the classes of Edouard, but this is standard deep learning machinery, or if you want, just optimization of a loss function. So you see that here I'm just using a mean squared error for evaluating the quality of my predictions. And then that's it. And then from time to time, I update my target network with the new thing, and then I evaluate the performance of the algorithm. So this is just to show that it's at the same time very different, but also very similar to what we have seen in the exercise. It's still Q-learning. It's just Q-learning with a slightly different update rule because it has a gradient to compute, but it has all the nice framing into a simple deep learning optimization problem, which makes it very flexible to be using, whatever technology comes out of deep learning. You can plug it in. It doesn't work, it's not if it works well in computer vision, it's not obviously it's going to work well in RL at all. But this is just to illustrate a little bit of what modern reinforcement learning looks like. So I'm really, there are a few questions. I noticed there is a problem with the links, the code from link 3, the same. Okay, so I will be updating the...
In fact, with your PDF, okay. It's okay, but it's just the links you send me, but it's changed, so it's okay.
Oh, yeah, it's changed because I changed it to a
no problem.
One.
So now on the web page, it's the right link.
Okay, great. So let me just maybe 1 minute in wrapping up. Sorry for rushing a little bit, but time is short. So things that we have not discussed, there are plenty. So the exploration and exploitation dilemma, I just mention it very quickly. Off-policy learning, there are things like imitation or apprenticeship learning, constrained RL, multi-agent RL. So the field of RL is broad and honestly fast-growing, even too much. I would say there is also too much hype around what RL promises and what it can actually achieve. But let's say that it's also very diverse and very complicated compared maybe to some other fields in supervised learning, in machine learning in general. And today we have impressive results whenever we have access to a simulator. Atari game, Go game, Alpha Star applied to StarCraft. It's very flexible and can leverage state-of-the-art deep learning techniques, so they can be plugged in. And I think we are also discovering more and more which problems can actually benefit from RL, like energy management, for instance. Google worked a few years ago on optimizing energy consumption in data centers, just to give an example, right? Which is not the most AI obvious problem that you might think about. And then I think a lot of literature now is also pushing about using RL as part of multimodal learning. Like, I receive as input an image, I'm communicating with humans through voice, and so I also have audio signals, and I can perform actions either in terms of communication or in terms of a robot. So there are a lot of multimodality happening in the perceptions and in the actions that we can do. Reality, and so this is just to break a little bit the hype, is that RL algorithms are incredibly simple and efficient. When you look at this simple complexity of the final version of the algorithms that we use to, I don't know, beat the best player in Go or in StarCraft. So just the training of, after we have done all the tuning and all the things, the best algorithm we have, and we just train it, it's just impressive the amount of time. We're talking about, millions of samples, millions of gains, which is not the speed at which humans learn. So there might be something to gain in there, and there is definitely something to gain. They're still very cumbersome to deploy. There is still a lot of art in tuning the parameters, in choosing the architectures. And even more importantly, it's super hard to deploy these things when you have real world problems. Because most of the time, if you have an autonomous car, if you have a recommender system, if you have a question and answer type of conversational agent, you need to be extra careful, right? There are plenty of constraints, can be privacy, can be safety, can be a lot of things that you might not have in standard supervised learning where you don't take actions, right? If I tag an image wrong, my performance maybe is not that great, but I'm not actually doing something in the world. Reinforcement learning, the promise is that you have an agent which does stuff in the environment in an uncontrolled way. So we are better be sure that what we do is safe, is reliable, is robust, it's able to adapt fast if the situation, the conditions change over time. So I think we're still far from being able to put these things out in the wild, or at least I hope that we will be conscious about putting these things out in the wild, unless the environment is super safe by definition, like a simulator. I really don't care. I can simulate it for millions of steps. I'm not doing anything bad. I'm just wasting time and energy maybe. But once I deploy a policy or I deploy a learning algorithm, I need to be really sure that what I'm doing is safe somehow and it's robust to the environment. Okay, so this is all for me. It was very rushed. Thank you very much for attending, and I'm happy to keep chatting for a few more minutes if you have any question.
Thank you very much.
There is already... Thank you. So there is already a question on the chat.
Yes.
Using images is RL robust respect to noise? So image-based RL is getting better and better. If you train it with noise, then I would say yes. So much so that most of the time when we do image-based RL, what we do is it's data augmentation. So we inject noise into the images that we observe while training the agent on purpose to make it more robust to noise in the real environment. And this, if you want, it's very similar to what is done in self-supervised computer vision, where you really generate images which are random perturbations like rotation, rescaling, changes in the colors of the true images that you have in the data set to make your algorithm more robust when you deploy it. If the question is it's robust with respect to just to throw something else to attacks, then no. It might be robust to, let's say, benevolent noise, but if you throw on purpose modified images, it's even more subject to adversarial attacks than normal deep learning technologies. So if you want the agent to start doing something different than what the policy should be doing by just changing the input, which are the states. So if I perturb a little bit the image in input and I want to kind of trick the policy to do something bad, that's quite possible. If you want, it's, everything in reinforcement learning is amplified. So if something is difficult or it's simple, inefficient, in supervised learning, in RL is worse. Adversarial attacks are bad in let's say computer vision, are even worse in RL. So I think, again, we're at the point where we're still learning how to do a good reinforcement learning algorithm that works pretty much without too much tuning and too much hacking. So we will think about these problems probably a little bit later. But there are people studying these questions already.